Today is the 6th still. And you've probably known since at least the 6th grade, if not before that, that matter is anything that has mass takes up space. And mass is just how much matter there is. Your mass never changes. Well, okay, your mass changes a lot. Your mass changes over your lifetime. But if I were suddenly winked to the surface of the moon, my mass would not change, but my weight would. Be very careful with the words mass and weight. We use them interchangeably here on Earth because our weight is consistent as long as the gravitational attraction that the Earth has for us is consistent, but our mass is really what's consistent. And weight is all based on gravity. You weigh less on the moon. You don't have less mass. So that's an important distinction. My goal is that by the end of the year, you feel uncomfortable saying you're weighing something. That's my goal for me, is that you can't say that comfortably, because I can't say that. Like if I step on the bathroom scale in the morning, I think, oh, okay, I got a mass reading. Even though it's set in pounds, it's really a weight, but I can't say I weighed it, because it's so, we should really be talking about mass. Anyway, that's the first bit. Now, you've also probably known for a very, very long time that atoms make up everything. Never trust them. There was a sort of a survey of scientists, this was 10 years ago or so, talking about if you knew that human civilization and all the things that we had learned were going to be destroyed, and you could only convey one idea to future civilizations that would arise from the ashes of what humans had done in the past, what idea would you convey? If you could scratch one thing on the cliff wall, for future explorers to find, and save them all the trouble of figuring it all out from scratch again, what would it be? And a shockingly large number of scientists, not just chemists, physicists, biologists, all other things, said that the most important idea they thought that they could convey to some future civilization that might arise from the ashes of the destruction of this one was the idea that all things are made up of tiny particles. Basically atomic theory, that everything we look at is made up of these tiny particles, because so much other stuff flows from that. We kind of take it for granted. Like when I think back, and I want you to actually actively try to think back to a point when you didn't know that. We just kind of accept it. It's the air we breathe. We know that everything's made up of little tiny particles. They vibrate. Oh, yeah, whatever. My 6-year-old can tell you that. We just accept that, but that hasn't always been well understood. We'll talk more about that when we do atomic history. They are the building blocks of matter. At one time we thought they couldn't be divided. And they are the smallest unit of an element that maintains the characteristics of the element. So a single atom of an element has the characteristics of that element. That's kind of important. So elements are pure substances. If you took this down to a single atom, which you couldn't do here in this room, it would be impossible, you would have a single atom of this element. What is this element? You can buy big sheets of it at the grocery store for 99 cents. What is it? Aluminum foil. Don't you dare say tin foil. Nobody did. That's good. It's aluminum foil, or as the Brits say, aluminium, which I just think sounds ever so sophisticated. It is an element. Aluminum is an element. It's on the periodic table. It's a metal. You can get down to a single atom of aluminum. And then we got this stuff. Why does she have a bag of water? Some of you know. I have a bag of water. Can I have an atom of water? No. Because water is a compound. It's chemically joined. It's hydrogen and oxygen that are chemically bonded to one another. I can break them up, but I can't do so under normal conditions. It's going to take a chemical reaction to break them apart. So the elements are the individual pieces of which compounds are made. Now, properties. properties of matter. And your book goes into a little bit more detail on this. I can post the section if you would like. You're also free to look at the section on your own if you would like. It's section 2 of chapter 1. But when we talk about the properties of matter, a property is a characteristic. A property of my shirt is that it's purple. A property of this floor is that it's green and it's rubberized to some degree. A property of this table at the moment is that it's colder than the air surrounding it. Those are all properties. They're characteristics of the item. A property of this table is that it is heat proof. I can put a hot dish down on it. It will not burn or discolor or stain. There are two broad categories of properties of matter. One is extensive, so external to the material itself. Extensive properties are dependent on how much stuff you got. Mass, volume, the amount of energy contained in a chunk of matter. Has anybody here ever been at a bonfire? I'm going to assign you homework if you haven't. Okay. So you've watched wood burn? You know what you're watching, right? Talk to one another. What are you watching when you sit around, sit in your camp chair, watching wood burn? What are you watching? Other than potentially stupid hijinks. I see the giggles back there. Potentially stupid hijinks from your friends. When you look deep into the fire, what is that beautiful light that reflects back out onto your face? Warms your heart, burns your sneaker soles if you're not careful drying your shoes. It's energy! Sunlight being released all at once. All that sunlight the tree ever absorbed in its whole lifetime being released back to you as heat and light. I love thinking about that. Does the amount of energy in a log depend on how much of the log you have? Yes. Twigs burn fast. Logs burn a lot longer. That's an extensive property, the amount of energy that's contained in something. The volume of something, the mass of something. Now, could we identify what kind of tree it was from how much energy was contained in it if they were all different sizes? No. Because the amount of energy contained in it is an extensive property. We don't have they're not as useful to us in a lot of ways. It's not that they're not important, they are, but we're mostly interested in which properties we can use to look at a substance and say, I know what this stuff is. So we want to think more in terms of intensive properties. And for intensive properties, it doesn't matter how much of the substance is there. The intensive properties are going to be consistent. So go ahead and look at that little piece of aluminum that I gave you. Doesn't matter if you have a very large chunk of it or a very small chunk of it or a few atoms of it. We could heat that aluminum until it melted, and the temperature at which it melted would be consistent no matter how large a chunk of it we had. We know that aluminum is conductive. It conducts electricity, the flow of electrons, very nicely. Doesn't matter if you got a little bit, doesn't matter if you got a lot. It's going to conduct electricity in the same way. The density of aluminum, we could ball up aluminum, big chunks, little chunks, press it down real nice, and figure out the density, the mass per unit volume of this aluminum, and it's not going to change. The density of aluminum is going to be consistent no matter how much aluminum we have. So if you're going to identify a substance, which one do you want to focus on? Intensive properties. And that's what we're going to talk about next. So I'm going to give you the next slide. We'll start the discussion, and then tomorrow after your lab practical, assuming we do get through it, we'll pick it up. Okay. We had a division of extensive, intensive. We have a division of intensive properties too. And the two types of intensive properties we have are chemical and physical. They're all intensive properties, but they are different. You probably did chemical change, physical change in physical science. Wood burning, chemical change. Aluminum foil being crumpled up, physical change. Something being cut, physical change. Something melting, physical change. Boiling, freezing, physical change. Physical properties can be observed without the substance undergoing a chemical change. You don't change the identity of the substance when you observe a physical property. If you melt a piece of ice, is it the same stuff you started with? Yeah. It was solid water, now it's liquid water. If you boil it and you capture the steam, is that the same stuff you started with? Yeah. Now it's gaseous water. If you melt the aluminum that I gave you, is it the same stuff you started with? Yeah, now it's just a liquid. Physical properties can be observed without changing what it is that you're observing. Chemical properties, on the other hand, because they're all about how easily, well, they're all about the substance undergoing chemical change. Does the substance react? If I take that aluminum foil that I gave you and I stick it in water, will it react? Will there be a reaction? Here, let's test it. I'll steal your aluminum, Tim. We're going to stick, watch out, Kaylee, I'm doing this right behind you. You're living on the edge. You didn't even know it. You didn't sign up for this. What the heck? Okay, do you think it'll blow up? Let's try! Of course not, you knew that. I wouldn't do that with you sitting there if I thought it was going to blow up. Okay, it doesn't do anything. It's not fizzing, it's not bubbling, it's not spinning around. It's non-reactive in water. You'll create a reactivity series later this year where you test the reactivity of a bunch of metals in water and in acid. Now, if I put that aluminum in acid, guess what would happen? It would start to fizz. I'm not going to do that. It would start to fizz. It would start to generate some hydrogen gas. We would see movement. We would see a gas being produced. We would see bubbles because it's reactive in acid. Reactivity is how readily a substance undergoes a reaction, and that is a chemical property. What if I held that aluminum in a flame? Would it burn? You've all put aluminum cans in the fire, I assume. You shouldn't do that. You should just recycle them. But if you've thrown them in the fire because it's cool, do they burn? No. They melt eventually. You might get a little bit of burning on some of them. In general, they're not terribly flammable. Flammability is a chemical property. When something burns, it changes substance.